Welcome to the course on an introduction to information theory. I am Adrish Banerjee and today we are going to talk about information inequalities. In particular, we will talk about what is Jensen's inequality and how this is used to find whether a function is concave or convex. We will talk about log sum inequality and we will show one example of how we can use log sum inequality to prove concavity or convexity of a function. Next we will talk about data processing lemma, and finally we will talk about Fano's lemma. So this lecture will talk about these inequalities and lemma. So let's start with Jensen's inequality. So before we go to Jensen's inequality, let's just see what do we mean by a function is concave or convex. So function f is concave over a non-zero interval I if for each point x0 which belongs to this interval I there exists a real number c such that this condition holds. Now what is this condition? So let's just draw, let's say this is a function defined over this interval from here to here. Now take any point belonging to this interval. Let's just take this point x0, and this is my function f of x. So what is f of x0? That is this point. This is f of x0. So there exists a real number c. Of course the value of c will depend on x0 such that function f of x is below f x0 plus c x minus x0. What is c x minus x0? It is a line passing through x0 and passing through this point. So this will be basically a line. This is a straight line passing through x0. Now note that this c, the slope of this line depends on what choice of x0 I choose. For example, if I choose this as my x0, then the slope is negative. So this is what the line is. So if the function is concave, I can draw a line passing through x0 and this function will lie below that. So that is what I mean by function is concave. Now if the function is convex, then what is going to happen is you will have a function like this. Let us say this is a function defined over this interval x1 to x2, and take any point. Let us just take this point x0. If I draw a line passing through this thing x0, then for the function to be convex, f of x should be above this line. This is the condition for function to be convex, okay, and this is the condition for the function to be concave. Now we will use this result to obtain Jensen's inequality, which says if the function is concave and we have a random variable x that takes values within the interval over which this function f of x is defined, or over the interval where the function is concave, then expected value of the function is less than equal to function evaluated at expected value of x. Now let us see at the proof of this. We will get the proof from this result. So if I take expectation both side, what do I get? F of fx, this is less than expected value of f of x0. Now what is f of x0? x0 is a number in the interval over which this function is concave. So expected value of f of x0 will be f of x0. plus c times expected value of x minus x naught. Now, if I choose my point x naught such that x naught is expected value of x, which is possible because x naught belongs to the interval over which this function is concave. So, I can choose my x naught such that x naught is expected value of x. Now, if I choose this value of x naught and I plug it in here, what do I get? I get expected value of f of x is less than equal to function. What is x naught? X naught is expected value of x, and c, this expected value of x minus expected value of x. So, this term will become 0. So, what I will be left with is this, and this is precisely my Jensen's inequality. So, if I have a function f which is concave, then this relation holds. Now, similarly, if the function f is convex, we can similarly show that expected value of f of x will be greater than equal to function evaluated at expected value of x. The proof is very similar to how we proved, starting from this result. Okay. So, this is our Jensen's inequality. Now, we will show some more ways of proving whether a function is concave or convex. So, if you have a function f which is concave over an interval I, then it is concave if and only if for every x1 and x2 which belongs to this interval I, this relation holds. What is this? This lambda times f of x1 plus 1 minus lambda times f of x2. This should be less than equal to function evaluated at lambda times x1 plus 1 minus lambda times x2, where lambda lies between 0 and 1. Now, using Jensen's inequality, we can prove this result. So, let us look at the proof. Let us say we have a random variable x, and that takes two values, x1 and x2. It takes x1 with probability lambda. So, x2 happens with probability 1 minus lambda. Now, what does Jensen's inequality says? The Jensen's inequality says if the function f is concave, then expected value of the function is less than equal to function evaluated at expected value. So, then let us compute expected value of the function. What is the expected value of the function? Expected value of the function is, so x takes value lambda 1, x1 and x2 with probability lambda and 1 minus lambda. So, the expected value of the function will be f of x1 multiplied by probability of occurrence of x1, which is lambda, and f of x2 multiplied by probability of occurrence of x2, which is 1 minus lambda. So, this is the value for expected value of the function f of x. Now, Jensen's inequality says if the function is concave, then function expected value of the function is less than equal to function evaluated at expected value of x. So, according to Jensen's inequality, this term will be less than this. Now what is expected value of x? So x1 happens with probability lambda and x2 happens with probability 1 minus lambda. So the expected value of x is given by this expression. This is your expected value of x. So then applying Jensen's inequality, we get this result. On the left hand side is expected value of the function, and on the right hand side is function evaluated at expected value. So if the function is concave over this interval, this relation holds, and vice versa, if the function is convex, then this relation would be greater than equal to. Okay. Now we will show another way of proving whether a function is concave or convex. So if we have a function f that has a second derivative, and this second derivative is non-negative over this interval over which function is defined, then the function is concave over that interval. So what do we need? We want the second derivative to be non-negative. Now how can we prove this? So we do a Taylor expansion of this function around x naught, where x naught is a point in this interval. So Taylor's series expansion, I can write as f of x naught plus first derivative of f evaluated at x naught, x minus x naught, plus second derivative of this function f evaluated some x star by 2 x by x naught, where this x star point lies between x0 and x. Now what am I saying? I am saying for function to be convex, I want the second derivative to be non-negative. So what I need to show is, if the second derivative is non-negative, then this function f of x is convex. So let us prove it. So we are saying that if second derivative is positive, then function should be convex. So if the second derivative is positive, then this last term is going to be, if this is non-negative, this is square of x minus x naught, so that is also non-negative. So this whole term will be non-negative term. So then what I can do is, I can write f of x to be, so since this term is positive, so f of x will be greater than equal, this is non-negative, so f of x will be greater than equal to f of x naught plus f first derivative of f evaluated at x naught, x minus x naught. So this follows from the fact that since this term is non-negative, this whole term will be non-negative, so f of x will be greater than equal to this term. Fine. So that is what I have here. Now let us take the value of x naught to be this, which is lambda times x1 plus 1 minus lambda times x2, and let us take x to be x1. So I plug in this value of x and x naught into this expression. So I get here f of x1 is greater than equal to f of x naught plus first derivative of this function f evaluated at x naught, 1 minus lambda x minus x naught, where x naught is given by this. Next I put x equal to x2. So I will put x equal to x2 in this equation. here I put x equal to x2. So if I similarly put x equal to x2, what I get is f of x2 is greater than equal to f of x naught, first derivative of f evaluated at x naught, lambda x2 minus x1, where x naught is again lambda times x1 plus 1 minus lambda times x2. Okay. Now what I am going to do is I am going to multiply this expression by 1 minus lambda, and this expression I am going to multiply by lambda. Okay. So equation 2 I am going to multiply by lambda, and equation 3 I am going to multiply by 1 minus lambda, and then I am going to add them up. So if I do that, what I get here is I get f of x naught is less than equal to lambda times f of x1 plus 1 minus lambda times f of x2. So again I repeat, if I multiply equation 2 by lambda and equation 3 by 1 minus lambda and I add them up, I get this condition that f of x naught is less than equal to lambda times f of x1 plus 1 minus lambda times f of x2. Now what is this? You go back to our previous expression that we had. We have said if the function is concave, then lambda f of x1 plus 1 minus lambda f of x2 is less than equal to function evaluated at lambda x lambda x2, and if the function is convex, we said lambda f of x1 plus 1 minus lambda f of x2 would be greater than equal to function evaluated at lambda x1 plus 1 minus lambda x2. Now go back and see what we have arrived at. We have arrived at the condition where function evaluated at x naught is less than equal to lambda f of x1 plus 1 minus lambda f of x2, and this is from the result which I have just shown you, this is the condition for the function to be convex. Hence we have proved that if the second derivative is positive, then the function is convex. So if a function has second derivative that is non-negative over the interval, then the function is convex, and if the second derivative is positive, then it is strictly convex. And similarly we can also show if the second derivative is non-positive, then the function is concave. So let us take some example to illustrate the Jensen's inequality that we have talked about. So use Jensen's inequality to find appropriate inequalities between expected value of this function e raised to the power minus ax and e raised to the power minus a expected value of x, where a is greater than equal to 0, and the second function that we are considering is expected value of under root x and square root of expected value of x. So in the first case this function is given by this. So we need to first find out, so we want to find out whether the function is concave or convex, and depending on whether the function is concave or convex, we can find relationship between expected value of the function and function evaluated at expected value, right. So in this case if we look at this function f of x, we take the first derivative, that is given by this, and the second derivative is given by this. Now note a is greater than equal to 0, so a square is basically positive, this quantity e of a minus x is also positive, so this term will be greater than 0. So if the second derivative is greater than 0, what do we know about the function? We know that the function is convex function. So then our f of x is a convex function, and it is a strictly convex function because the second derivative is positive. Okay. Now if it is a convex function, then we know the expected value of the function is greater than equal to function evaluated at expected value of x. So for this particular function we can write expected value of the function is greater than equal to function evaluated at expected value. This is because this function was convex function. Now let us look at this second example. So here the function is under root of x. Now we take the first derivative, that is given by this, and this is the second derivative. Now the second derivative is non-positive, so that means this is a concave function, and if it is a concave function, then we know expected value of the function is less than equal to function evaluated at expected value. So what is the function here? Function here is under root of x. So expected value of under root of x will be less than equal to, now the function is under root x, so that means under root and function evaluated expected value of x. So this expected value of under root x will be less than equal to under root of expected value of x. Okay. Now let us just move now to log sum inequality. So what does log sum inequality says? If you have non-negative numbers a1, a2, a3, an let us say, and b1, b2, b3, bn, where summation of these ai is bounded and summation of this bi is greater than 0 and again it is bounded, then log sum inequality says that summation of ai log ai by bi is more than is greater than equal to summation of ai log of summation of ai by summation of bi. So this is basically your log sum inequality. Now let us prove this. So let us consider ai dash, which is ai by summation of this ai's, bi summation of these bi's. Now let us find divergence between ai dash and bi dash. Now what do we know about divergence between two density functions? Basically we know the divergence is greater than equal to 0. So divergence between ai dash and bi dash would be greater than equal to 0. So this we are writing it here. This is the expression. So this is the expression for divergence between ai dash and bi dash, and we know that this divergence is greater than equal to 0. This we have proved in the earlier lectures. Now let us replace ai dash and bi dash in this expression. So ai dash is given by this and bi dash is given by this. Okay. So we plug in these values of ai dash and bi dash, what we get is this expression. You can see this is my ai dash, this is my ai dash, and this is my bi dash. Okay. Now further simplifying, I take this summation ai off. So what I get here is summation of ai log ai by bi minus summation of ai log of summation of ai's divided by summation of bi's. Now I know this is greater than equal to 0. Now this is sum of non-negative numbers, so that is a positive quantity. So when will this be greater than equal to 0? When this term is greater than equal to this term. Okay. So, what we have proved here is now then this relationship holds, and this is known as log sum inequality. Now, let us take a simple example where we will prove that divergence is a convex function in the probability pair P and Q, and we are going to make use of log sum inequality to prove this result. So, we want to show that divergence between P and Q is a convex function in the pair P and Q. So, what do we mean is, if P1 Q1 and P2 Q2 are two pairs of probability mass function, then function evaluated at x naught is less than equal to expected value of the function. This is when the function is convex, right? When the function, we have just showed that function at expected value of x is less than equal to expected value of function. This is for the case when f of x is convex, right? This is from the Jensen's inequality. So, to prove that this is a convex function, we have to then, from Jensen's inequality, we have to show this result where lambda lies between 0 and 1. So, let us see how we can make use of log sum inequality to prove this result. Now, we are applying log sum inequality. Now, what does log sum inequality says? The log sum inequality says summation ai log of ai by bi, this is greater than equal to summation ai log of summation ai by summation pi, right. Now, let us take A1 to be lambda times P1 x and A2 to be 1 minus lambda times P2 x. Similarly, let us take B1 to be lambda times Q1 x and B2 to be 1 minus lambda times Q2 x, and plug in these values of A1 A2 and B1 B2 into our log sum inequality. Okay. Then according to log sum inequality, summation ai log summation ai by summation bi is less than equal to summation of ai log of ai by bi. So, what is summation ai? This is this plus this. So, this is this quantity. What is summation ai? So, log of summation ai is this quantity. And what is summation bi? B1 is lambda q1x and B2 is 1 minus lambda q2x. So, this is my summation bi. Now, according to log sum inequality, this summation is less than equal to summation of ai log ai by bi. So, this summation is less than a1 log a1 by b1 plus a2 log a2 by b2. So, what is a1? This is my a1 and this is my a1, this is my b1, this is my a2, this is my a2 and this is my b2. So, this result which I have written so far is just a direct application of log sum inequality, where I chose a1 to be given by this, a2 to be given by this, b1 to be given by this and B2 to be given by this. So if I do this using log sum inequality, I get this result. Now what is the next step I do? I sum it over all x. So I sum it over all x, sum it over all x, sum it over all x, sum it over all x. So what do I get here? You can think of a new probability which is lambda p1 x plus 1 minus lambda p2 x, and there is another new probability lambda q1 x plus 1 minus lambda q2 x. So this quantity that you see here, this quantity that you see here is nothing but this divergence between this probability and this probability. So the term that you see on the left hand side is nothing but this term. What about this? This is lambda p1x log of this lambda cancels out. So this is lambda times p1x log p1x by q1x, sum over x. This quantity is nothing but this quantity, lambda times divergence between p1 and q1. What about this quantity, second quantity? It is 1 minus lambda times p2x log this 1 minus lambda cancels out, this is p2x log of p2x by q2x, summation over x 1 minus lambda times. So this term will be 1 minus lambda times divergence between p2 and q2. So using log sum inequality, we have shown that this relation holds, and from Jensen's inequality we know this is the condition for this function divergence to be convex in the pair P and Q. Okay. Now let us use these results to prove some more results on concavity and convexity. So let us prove that entropy is a concave function of P. Now in the previous lecture we have shown, when we have defined divergence between two random variables x and x hat, where x hat was uniformly distributed, we have shown that entropy of P is basically log of L minus divergence between P and uniform distribution. Now we have already shown in the previous slide that divergence function is a convex function. So minus of a convex function will be a concave function. So then from the previous result it is very clear that entropy is a concave function of P. That is because this is just a constant, and minus of a convex function will be a concave function. So as a function of P, H of P, entropy is a concave function. So this result follows from the previous result that we have shown, that divergence is a convex function. So the concavity of entropy function follows from the convexity of the divergence function. Now let us prove and state what is known as data processing lemma. So data processing lemma says that if we have the random variable x, y and z, and if they form a Markov chain, then mutual information between x and z is less than mutual information between x and y, or mutual information between x and z is less than mutual information between y and z. So in other words, further processing of data does not increase the information content. So how do we prove it? So we are first going to prove, so let us just prove. So since x, y and z forms a Markov chain, then we use the property of Markov chain. So probability of z given x, y will only depend on probability of z given y, because x, y and z forms a Markov chain. Or in terms of entropy, we can write uncertainty in z given xy is same as uncertainty in z given y. This follows from the point that x, y, z forms a Markov chain. So let us write down the mutual information between y and z. Now following the definition of mutual information, we can write, so this follows from the definition, this follows from the definition. So mutual information I can write as h of z minus h of z by given y. Now from this I know h of z given y is same as h of z given x and y. So I replace this h of z given by this uncertainty in z given xy. Okay, so this line follows from here, Markov process. Now I know that conditioning cannot increase entropy. So uncertainty in z given xy is less than equal to uncertainty in z given x. This follows from the property that conditioning cannot increase entropy. So if I use this relationship and replace uncertainty in z given xy by a larger term h of z given x, so what I get here is greater than equal to sign, and I am replacing this by h of z given x. Okay, and what is this term? Uncertainty in z minus uncertainty in z given x, that is mutual information between, this is from the definition, this is a mutual information between x and z. So what I have shown you is mutual information between x and z is less than equal to mutual information between y and z. When x, y and z forms a Markov chain. So I have shown you this, I have proved this result. Now how do I prove this result? Now if you see closely, if I can show that if x, y and z forms a Markov chain, then it also follows that z, y and x forms a Markov chain, then I can use the previous derivation to show that mutual information between z and x. If I can show that this implies, if I can show that x, y and z, if they form a Markov chain, then z, x and z, y and x also forms a Markov chain. If I can prove this, then from the previous result which I just now proved, I can show that mutual information between x and z will be less than mutual information between x and y, because I just now showed you that if x, y and z forms a Markov chain, then mutual information between x and z is less than equal to mutual information between y and z. So to prove this result, it is sufficient to prove that if x, y, z forms a Markov chain, it implies that z, y and k also forms a Markov chain. So we will show now that if x, y and z they form a Markov chain, then z, y and x will also form a Markov chain. So to prove this, we will first consider the joint entropy of x, y and z, and applying chain rule we can write this as uncertainty in y plus uncertainty in x given y plus uncertainty in z given x y. Now since x, y and z they form a Markov chain, we know that uncertainty in z given x y is same as uncertainty in z given y. Okay. So we can write this joint entropy between x, y and z as h of y plus h of x given y plus h of z given y. Now we are writing this joint entropy again using chain rule in a different way. So I can write the same thing as h of y plus h of z given y plus h of x given z y. Now let us compare, this is joint entropy given by this expression and this is joint entropy of x y z given by this expression. So let us compare these two equations. This is a common term h of y, it is here, it is here. Then I have a common term h of z given y, I have a common term here h of z given y. So if these two are same, what do I get? I get this condition that this term must be equal to this. So in other words, uncertainty in x given yz is same as uncertainty in x given y, and this is true when, so in terms of probability I can write probability of x given yz is same as probability of x given y. So when is this true? This is true when z, y and x form a Markov chain. So in that case probability of x given yz will only depend on probability of x given y. So what I have shown you is, if x, y and z forms a Markov chain, this also implies that z, y and x also will form a Markov chain, and hence using the proof that we just said before, we can write that mutual information between x and z is less than equal to mutual information between x and y, and this proves our second result that we had. This proves our result that mutual information between x and z is less than mutual information between x and y. So this is our data processing lemma. Now finally we are going to state and prove what is known as Fano's lemma. So we have a random variable u, let us denote u hat is the estimate of this random variable u, and we define probability of error. So when does an error occur? An error occur if our estimated bit is not same as the transmitted bit. So if u hat is not same as u, error happens, and probability of that will give you probability of error. Now what does Fano's lemma says is as follows: if u and u hat are Ellery random variables and probability of error is given by p sub e, then this relation holds. The binary entropy function of, well, the entropy of this P plus P log of L minus 1 is greater than equal to uncertainty in u given u hat, and the equality here happens if and only if probability of error given u hat is u is same for all u, and if there is an error, all L minus 1 erroneous values are equally likely to happen. So Fano-Lemmas links probability of error to the estimate of u that we are getting, uncertainty in u given u hat. So let us prove this result. So let us denote a random variable z, which basically denotes or indicates whether there is an error. So this random variable z, which is an indicator random variable, will be 0 if there is no error, and this will be 1 if there is an error. So z takes two values, either 0 or 1, 0 when there is no error and 1 when there is an error. So what is the entropy associated with z? So we can see basically, so z takes two value, so with probability 1 minus p this thing happens, there is no error with this probability, and with this probability there is an error. So then the entropy of z will be given by minus of Pe log Pe minus 1 minus Pe log 1 minus Pe, which is nothing but entropy of Pe. Okay. Now let us look at this term, uncertainty in u z given the estimate of u. Now we apply chain rule. So this, if we apply chain rule, what we get is uncertainty in u given u hat plus uncertainty in z given u hat is equal to this quantity. Okay. Now let us look at each of these two quantities. What is the uncertainty in z given u hat? Now what is z? Z is an indicator random variable which indicates whether there is an error, and it depends on what is the value of u and u hat. So if you tell me what u and u hat are, I can easily find out what is z, because if u is same as u hat, z is 0, and if u is not same as u hat, then z is 1. So there is no uncertainty in z given u hat. So this term is 0. Then I can write this term is equal to this. Fine. Now the same thing I am writing. So this expression I get from here. Okay. Now again I apply chain rule. So uncertainty in u z given u hat can be written as uncertainty in z given u hat plus uncertainty in u given u hat z. Now uncertainty, we know that conditioning cannot increase uncertainty. So h of z given u hat has to be less than equal to h of z. So then I can write this as this term is less than equal to h of z plus h of u given u hat z. And when is this is same? When basically when u hat is independent of z. So in other words, when this condition holds, when probability of error is same irrespective of what u is, then h of z given u hat will be h of z. So from here to here it follows from the fact that conditioning cannot increase entropy. Next, we are going to look into little more detail to this expression. So let us look at this expression. So we will first look at this when z is 0, and then we will look at the case when z is 1. So what is the uncertainty in u given u hat and z is 0. Now what does z equal to 0 means? Z equal to 0 means there is no error. So if I give you u hat and I tell you there is no error, then you know precisely what is u. So there is no uncertainty in u given u hat and z equal to 0. So then this uncertainty is 0. What about when z is 1? When z is 1, this corresponds to the case when u is not same as u hat. That means an error has happened. So in this case you know that u is not equal to u hat, but you do not know which of the remaining L minus 1 possibility. Okay. So you know that u can take any value except u hat when z is 1, and we know that if you have a discrete random variable, the entropy is upper bounded by number of possibilities of x. In this case, number of possibilities for u is L minus 1, because u is not same as u hat and u is a L valued random variable. So this entropy is upper bounded by log of L minus 1. So if I plug that in, then the uncertainty in u given u hat and z can be written as probability of z equal to 1, uncertainty in u given u hat and z equal to 1 plus probability of z equal to 0 and uncertainty in u given u hat and z equal to 0. Now this uncertainty is 0, so the only term that will be left is probability of z equal to 1 multiplied by uncertainty in u given u hat and z equal to 1, and this quantity we just showed is upper bounded by this. So we plug this value in here, what we get is probability of z equal to 1, that is basically probability of error, and this is log of L minus 1. So what we have shown is this quantity is upper bounded by this quantity. Okay. Now when is this equal to this? When all the errors are equally likely to happen, we know that h of x is equal to log of number of possibilities of x, that is when this is uniformly distributed. So when all the L minus 1 possibility erroneous possibilities are equally likely, then this happens with equality. So in this expression of h of u given u hat z, we can plug in this upper bound. If we do that, what we get is this expression. So again, let me just go back. We had this expression, right? H of u given u hat is less than equal to h of z plus h of u given u hat and z. We have shown h of z is given by h of p, and we showed that this quantity is upper bounded by p log of L minus 1. So if you plug these values, this is h of p. If you plug these values in, we get our Fano's lemma, which is this. Note this is a convex function of p, this is a linear function of p, so sum of a convex function of p and a linear function. So this is what is our Fano's lemma. Okay. Now we can also get a weakened version of this Fano's lemma. We know that h of p is upper bounded by 1, so we can get a weaker version. If we just replace this by 1, we can also say 1 plus pe log of L minus 1 is greater than equal to h of u given u hat. So, this relates probability of error to the uncertainty in estimation of u. Thank you.